Hello and welcome to a lecture series on vibrations and sound. This course will serve as an introduction to the concept of mechanical vibrations as well as an introduction to sound. So this lecture series will cover 12 chapters. First, we will look at an introduction to vibrations. We will study single degree of freedom systems, damped free vibrations of single degree of freedom systems, forced vibrations of undamped single degree of freedom systems, forced vibrations of damped single degree of freedom systems, non-harmonic periodic forcing functions, transient vibrations. We will study multiple degree of freedom systems, as well as approximate methods for these multiple degree of freedom systems, vibrations of continuous systems and approximate methods for continuous systems, and then leave off with an introduction to the concepts of sound and acoustics. So this video is an introduction to vibrations. So why study vibrations? Well, vibrations can lead to excessive deflections and failure on the machines and structures. To reduce vibrations through proper design of machines and their mountings, it's important that we study vibrations. Many human activities involve some form of vibration. There are also some examples where things have gone quite wrong in various structures due to excessive vibrations. So I'm going to show a video here. This is an example of a very famous, this is an example of a very famous bridge collapse, the Tacoma Narrows Bridge, which collapsed in 1940 due to excessive vibrations induced by the wind. So I'll just play the video here too, so you can see what happens.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Here's another example where this is a soccer game where the fans are jumping as they're cheering, and you can see how the frequency of their jumping induces significant vibrations in the structure of the stadium. So you can see that it's important to have a good understanding of the dynamic behavior of these structures when designing them, and in order to keep the design safe. Here's another famous example. This is the Millennium Bridge in London that opened in 2000. So it was a pedestrian bridge. The bridge's movements, and I'll show the video in the next slide. But when the people started walking across the bridge, the pattern of their steps introduced some sway in the bridge, and then people started kind of walking in step with the frequency of the vibrations, which just continue to maximize the sway of the bridge. And so you can see what happened there. So let's just play this video. So in the day that this bridge opened, 90,000 people crossed the bridge, with up to 2,000 people on the bridge at any one time. And the case that the lateral motion caused by the pedestrians directly participated with the bridge, and so the vibrational modes had not been anticipated by the designers. So you can see that it swayed up to 70 millimeters kind of at its max. So those are some examples of when it's important to understand vibrations to keep things safe, so we don't have excessive vibrations. In other situations, it's useful to understand vibrations is as a necessary feature. So we need to understand vibrations for both extremely large structures as well as very small structures. So for example, in like a MEMS circuit, understanding vibrations and using vibrations is really important for their function. So in many of these cases, the goal of the engineer is to minimize or reduce the level of vibration, or design the machine or structure to withstand the vibrations to which it will be subjected. So we can think about things like shock absorbers, vibration isolation systems, etc. Other times we need to actually increase the vibrations, for example, in sound systems, accelerometers, clocks, vibration conveyors, and MEMS systems. There are lots of applications of vibration, as we've seen in bridges, in structures, so tall buildings, in machinery, rotating machinery, in understanding the effect of earthquakes on structures. This here is a tune mass damper that is in one of these, one of the tallest skyscrapers. It's in Taiwan. It's the largest tune mass damper, and it's actually visible to the public and used as an aesthetic feature as well as a structural feature. It helps to reduce the sway of the very tall building under wind loads. Other applications of vibration are in automotives, in clocks and watches, in various electronics. Of course, there's application of vibration in sound and acoustics, sound systems, musical instruments, as well as hearing aids or hearing amplification, and in motion or activity trackers like Fitbit or other types of trackers, all use vibrations in some way or in another. This is an example of vibration in my own research, where we use vibration analysis technique to understand the stiffness of the connection between an implant and the bone. So in this case, it's applied to an implant that is used to attach a bone conduction hearing aid, which again is another application of vibrations. So a bone conduction hearing aid, if a patient cannot tolerate a traditional in-the-ear hearing aid, you can put a small screw in the bone behind their ear and attach the sound processor there. So the sound is conducted to the cochlea through vibrations in the skull. And this connection is achieved through something called osseointegration, where the bone actually grows onto the implant and they become connected together. So one of the applications of my research is to use vibration analysis to understand how well integrated these implants are. So with these types of implants, there's always something that kind of pokes through the skin that we can access. So in this case, it's the abutment that you attach the sound processor to. So we can strike this abutment with a handpiece that can measure the acceleration response. So we get something that looks like this for the acceleration response, and this is a free vibration response of the system. We can use the techniques that we're going to learn in this course to develop an analytical model of the system, where we have things like the mass and the inertia properties of the implant and abutment system. We've got some estimates of various stiffness parameters, and the only unknown in the system is the stiffness of the bone implant interface, which we want to determine. So then we can use numerical analysis techniques to actually take the model response, so the acceleration of the impact rod from the model, and match that to the acceleration that we actually measure from the physical handpiece. And this gives us an estimate of this interface stiffness that we want to know. And this is just a video showing a finite element model, a dynamic simulation of this same technique, where this is the abutment and this is the impact rod striking it. So you can see what happens under this dynamic analysis, and this finite element model was used to help to evaluate our analytical model. So let's talk a bit about the basic concept of vibration. So vibration is any motion that repeats itself after an interval of time. So a simple vibratory system consists of a spring or some sort of elasticity element, a mass or some sort of inertia element, and a damper or some sort of dissipation element. And it involves the transfer of potential energy to kinetic energy and back again. So this is showing some very simple, the simplest vibration systems. So the black one here is an undamped spring mass system. The blue one here is a damped spring mass system. And then this shows just the position of the mass over time. So you can see that we get this oscillatory behavior, which is what we're going to see over and over throughout this course. Another very simple vibration system is a simple pendulum, as you can see here. And so if we look at the angle describing the location of this mass, over time, we would get this very similar oscillatory behavior. So vibration analysis is transferable to non-mechanical structures, even though we're going to focus mostly on mechanical structures in this course. Electrical and fluid systems also have the ability to resonate and transfer energy between different domains. For example, an inertia element is analogous to a capacitance element. A spring element is analogous to an inductance element, and a damping element is analogous to a resistance element. It's important to talk a bit about some terminology. So a degree of freedom, or DOF, is the minimum number of independent coordinates required to completely determine the positions of all parts of a system at any instant of time. So these are examples of single degree of freedom systems. So here we have a simple spring mass system with linear motion. So the coordinate X can completely describe the position of this mass at any given time. In a simple pendulum, we have this rotational motion where the coordinate theta can completely describe the position of our mass at any given time. So a single coordinate means it's a single degree of freedom system. We can also have a different type of rotational motion, like a torsional system, where again, this angle theta is enough to just completely describe the position of this inertia element, or this mass at the end of this rod, at any given time. So if we have a single coordinate that can completely describe our system, we have a single degree of freedom system. If we need two coordinates to completely describe our system, then we have a 2 degree of freedom system. So these are examples of 2 degree of freedom systems, where here I would need, for example, the position of both mass 1 and mass 2 to be able to fully describe this system. Here we can also combine rotational and linear motions or coordinates. So here I could have the position of the mass X as well as the rotation of this pendulum theta to completely describe this system. And here we can have, say, 2 different angles, so theta 1 and theta 2, to describe this system. And these are examples of 3 degree freedom systems. So again, we can, if we need 3 coordinates to completely describe our system, then we have a 3 degree of freedom system. So again, these are very similar examples: linear motion, some rotational motion, and some torsional motion. And if we have an infinite number of degrees of freedom, then in order to describe our system. So for example, a cantilever beam may fall into that. Then we actually have what is called a continuous system or distributed system, if an infinite number of degrees of freedom are required. So the first ones that we saw where a finite number of degrees of freedom are used, those are termed discrete or lumped parameter systems. In general, we can get more accurate results by increasing the number of degrees of freedom that we use. But it's important to note that we always want to use the simplest system possible that is able to describe our physical system. So if we can, so single or multiple degree of freedom systems can do an excellent job of describing many systems, even though they are continuous in real life. But there are some systems where we need to model it as a continuous system, and we can do that. And we will talk about different methods for those types of approaches.